In our last video, we showed that when you create a unit cell, we give the code a unit cell like this, as simple as this. The code doesn't view just the two atoms you've created, but it sees it as an endless number of atoms. So how does the code see this input file? If you go to boundaries, you can change this to, let's say, 3 by 3, and you see how the code is going to replicate this and in the simulation. So even though you created this basic unit, the code is going to multiply it this way and treat the simulation as an extended bulk atom in a simulation. But we don't only consider periodicity for bulk materials like this, we also cleave surfaces. And what's that all about? So that thing to speak about before I leave is the lattice constant. So you're going to hear a lot of times lattice constant, lattice constant. The lattice constant is the dimensions. So we said particles, the bases are arranged at the vertices, and the distance between the particles at the vertices A, B, and C is the lattice constant. So you have lattice constant A equal to B equal to C for the cubic system here. So ABC is the lattice constant, and then we also have the angles alpha, beta, and gamma. But the lattice constant is A, B, and C, and you come across that when you are cleaving surfaces, when you are describing unit cells. And just before we go, let me explain how surfaces are also cleaved. So in surfaces, let's say if we want a particular surface, we cleave them out of the unit cell. So let's take a simple cubic, and the bases at the the bases at the BCC. Okay, so you have the X, Y, Z axis. Whenever you cleave the axis perpendicular. You create a plane perpendicular to the axis. So this being the Z axis, if you cleave the material this way, you're going to intersect the the Z axis. So this is, when you cleave it this way, it's going to be, you're cutting the lattice, the Z lattice, into half, right? So you first have to find out where the plane or the lattice is intercepted. Okay, so for the Y and Z, it intercepts them at infinity. It doesn't touch them, so it's at infinity. For the Z axis, it cleaves it at the half, right? Half of the lattice. So this is half. So you have half, and then 1 over the intercept. So 1 over infinity, 1 over infinity, 1 over, so this gives you 2. Gives you 1 over infinity goes to 0. So this is a 0, 0, 2 plane. Imagine that you are going to intercept the Z axis, but at the position of 1. So this is the origin. So this is 1 at the position of 1, being the lattice constant 1. So this one, x, y, z, will give us x at infinity, y at infinity, and then z at 1. So if you do 1 over infinity, 1 over infinity, 1 over 1, then we get the 0, 0, 1 plane, and you can repeat that. So if you were to do x, y, z, and you have a plane that intercepts x and y, okay, so x and y, it cuts this way. So you can see that it intercepts both the x and y at 1, but it does not touch the z, that plane. So the plane here intercept x and y, but does not touch the z axis. So x is going to be 1, y is going to be 1, and this will be infinity. And 1 over 1, 1 over 1, 1 over infinity. So this will give you the 1, 1, 0 plane. And you can keep going on and on. This being the x-axis, you can also cleave it halfway. Okay, so halfway, and x, y, z, x is going to be halfway, y is going to be infinity, infinity. So 1 over everything gives us 2, 0, 0 plane. So these are the various ways you can cleave the surface to generate the surface you want. And like we said, after you have the surface, you have to add a vacuum to isolate it at least along one dimension. If you want a two-dimensional surface or one-dimensional, you decide and add a vacuum on the number of axes that you need to. So that's how important periodicity is. So for you to have a surface, it's usually two-dimensional, but the surface can also be three-dimensional if you make it as a slab that is really thick, so that the z-axis will be greater than the nanoscale, greater than 10 angstrom, and the y, the x and y, there's no vacuum, so they are going to be equally extended. So what happens due to periodicity? So because of this periodic nature, we always have to create supercells to isolate the adsorbate that we are creating or the impurity that we create. So if you create a unit cell like this, and the dimension is small, let's say about 2 angstrom, if you have impurity, good atom, is going to create another impurity, good atom, another impurity, good atom. And because you have just 2 angstrom, the distance between this and this atom will be short enough for them to interact. It's not going to be greater than 4, so they are able to still interact with each other. But because you want a very isolated impurity to see how the impurity actually impacts the normal atoms, you have to create a supercell, make it large enough, about 5 angstrom, so that if you have one impurity here, normal atoms, one impurity here, the distance between this is going to be isolated enough for you to see the effect between the dopant and the normal atoms. And the same thing, if you create a surface and you bring a molecule onto it, imagine that the unit cell itself has just a dimension of 1 angstrom, and is going to replicate, the code is replicating this unit, is going to create another 1 angstrom and bring the adsorbate onto it and create, imagine another periodic unit here. And because of this short distance, 1 angstrom between them, your measurement is not just going to be how CO interacts with the slab, but it's also going to have some repulsive and interactions between the adsorbate themselves as well as the material. So that will not give you a realistic simulation. So the best thing would be to create a big enough supercell, about 4 angstrom, so that if the code creates a periodic unit here, the molecules themselves will be very far away. And because they are more than 4 angstrom, they are definitely isolated. And the interaction you're going to report to be the actual interaction between the molecule and the material before saturation. So let's see what happens when we move atoms. Okay. So because of the periodic boundary condition, we see that if you have sodium chloride here, the code is going to replicate it this way. So you're going to have another sodium chloride and another sodium chloride this way. What happens is that if chlorine shifts out of this cell to the right, the chlorine here will also shift into this cell because of the periodic boundary, and the chlorine here also has to shift to the next cell. So whatever atoms you lose from the right hand side will appear from the left hand side. It's coming from the periodic image. And so if you do, let's say, an adsorption of hydrogen molecule, and the hydrogen is here, and the next hydrogen enters the next cell, it will disappear from your view and appear within the unit cell because of the periodic boundary conditions you've set. Once it goes out of your unit cell, it has to appear on the other side, because as this one is leaving, the periodic image on the left side is also leaving to your cell where you have your view. So in this case, how do you measure the distance of separation of your adsorbate? What you should have done is to just use the code to check distance between hydrogen and hydrogen, and let's say if it's 2 angstrom, you get the results. Now that the atom is displaced here, you don't have to report the distance here. It's going to be inaccurate. So what you do is to take the dimensions of the cell. So let's say if it was 5 angstrom being the dimension of your cell, you take 5 angstrom minus the distance between them. And if this one is 3 angstrom, that will give you 2 angstrom. That's the actual distance between the two particles. And the only reason why you are seeing such a big gap is because you are not looking at the actual molecule but its periodic image. Okay, the actual molecule has moved into the next cell. Or you can take it to mean that because the number of particles are conserved, they should not reduce. So when you lose from one side, you have to gain from the other side. Okay, so that brings us to the end of this video. Okay, so now I have two files. One of them has a bigger supercell with a lattice constant of 5.7, 5.7, 5.7. And I have another file which has a lattice parameter which is smaller, 2.8, 2.8, 2.8. And they both have calcium in there as an impurity. So let's visualize to see the difference. So we go to Vesta and let's go to File, Open. I have my files on desktop. So let's open the smaller one first, ion.vasp, and open that. Okay, so we see this how the impurity is going to look, but we can extend to see the periodic units, how the code is actually reading your structure. Sorry, okay. Right, so this is how concentrated the material actually is that you created, and we can open. Here we go. And we have this. So this is much more realistic to mimic reality. But let's replicate. So the code will actually see an extended version. So let's make it a 2 by 2. And okay. Yeah, so if we measure, you see the dopants are actually isolated. The code doesn't constrain them and force them into a concentrated distribution. And let's check the position here. So this 0.5, 0.5, and this is 2.8, 2.8, 2.8, and then 8. So that's about 6 angstroms apart, right? And the first one, let's check again. Here we have 1.4, 1.4. 1.4, 1.4, 4.2. So that's about 2 angstroms. So this is 4.2 and this is, so it should be 4.2 minus 1.4. So that's about 2 to 3 angstroms apart, which is not ideal.